In the previous video, we assessed the data that are available about your compressed air system. We'll now look at the second step of the structured approach to estimating energy savings, how to use the data you have to establish an energy consumption baseline for your compressed air system. This will help ensure that you can compare any energy savings estimates against total energy consumption and ensure you're getting reasonable results. To establish a complete energy baseline for your compressed air system, you'll need 4 things. First, you need to know how much power your compressor draws at different loads. And second, you need to know the compressor's operating profile, how much time the compressor spends at these different loads. Combining the two gives you the total energy consumption baseline of your air compressor. In addition to total energy consumption, it's good to know the demand your compressed air system is servicing, specifically the discharge pressure and average flow. This is important because estimating energy savings may require you to establish where you were on your compressor's performance curve before and after those changes. The easiest way to measure total energy consumption is to measure and log 3-phase power of the compressor continuously. With those data available, you can easily review historical energy consumption. When establishing your system's profile, a full 12 months of data are ideal to capture all modes of operation and any seasonal variations or production changes. If you don't log 3-phase power, current measurements or amps can be used to calculate 3-phase power. You can also use measured amps and information from the compressor kg to estimate power as a % of full load amps. Note that this is not accurate below 50%, as the power factor degrades at lower current draws. You'll also need data on the load factor and duty cycle of your air compressor. It's important to understand the current capacity level of your system to understand the impact of changing that capacity level. The best option is to have a meter measuring and logging the total flow generated by your air compressor. If you don't have metered data, your next best approach is to make a reasonable estimate of the load factor and duty cycle. To estimate the load and duty cycle, start with the compressor status logs. These data can include total running hours and loaded hours. If your compressor doesn't have a status log, you can use a simple on-off motor logger or a stopwatch during operating hours to time the length of the load and unload cycles. Your measurement should last long enough to get a representative sample of cycles. If your compressor is controlled by a variable frequency drive, check to see if the drive has motor speed log. Some may have a pulse output that can be connected to a data logger. If not, you'll either need to install a portable power meter or flow meter, or use an assumed load profile, which can have a high level of uncertainty. Once you have an estimate of the load profile or duty cycle, you can estimate the average power consumption of your air compressor. If you have a 2-stage compressor, refer to your compressor's kg sheet for the total package input power at 0 flow and the total package input power at rated capacity and full load operating pressure. Combine these with your compressor's duty cycle and total operating hours. You can then use the average load factor of your compressor to estimate the average input power using the characteristic curve from the kg sheet or a generic version. Average load factor can be calculated by dividing average flow by full load flow. If all you have is the motor nameplate and you just need a rough estimate, you can use this power equation to calculate average power using an estimated load factor. Once a reasonable baseline has been established, the next step is to determine the savings mechanism of your energy savings opportunity to understand how these changes might affect your baseline energy consumption. In the next video, we'll look at different savings mechanisms for compressed air systems.